Good morning, everyone. My name is Oscar Sumano, and I'm responsible for the on-prem Kubernetes platform at Morgan Stanley. I'm here with my team, Fernando Fraga Rodrigues, core platform engineer, and Arvin Amirian, senior principal consultant at Red Hat, and has been part of our Morgan Stanley engineering team for a few years now. This talks about how we scale OpenShift at Morgan Stanley. The name of our platform is called MKS, and it stands for Morgan Stanley Kubernetes Service, and we have been working on it for over 6 years now. We made the platform generally available over 3 years ago, and now we have it deployed across 16 data centers in North America, EMEA, and Asia. We set out to build a platform with security and compliance in mind because we're in a highly regulated industry. Scale and stability was core to our design, and now we have over 400 OpenShift clusters globally. We also set out to build common tooling for our users so they can have a consistent user experience when interacting with on-prem and public cloud Kubernetes clusters. In this section, we'll be focusing on the platform architecture. Our OpenShift cluster design is based on physical servers, and we've created rack designs in our data centers that have allowed us to scale as more capacity is required. To allow us to scale, we created 3 different cluster types with 3 different rack designs. Some of the key design drivers were, 1, the placement of the worker nodes and control nodes needed to be in the same availability zone for networking purposes, a constraint we had on the networking side outside of Kubernetes. The second thing was the storage layer based on iSCSI needed to be in proximity. Also, the failure domain for a single control node needed to be a physical rack. And the last thing is virtualizing the control plane nodes was an option because the compute requirements were only 4 cores and 32 gigs of memory. We ended up with this design that allowed us to separate areas of concern. The control nodes for customer clusters were distributed across multiple OpenShift clusters, which we call infrastructure clusters. KubeVirt was a perfect solution for this requirement, and we've been using it since day 1. This makes our design based on KubeVirt for the control nodes highly resilient, saves us data center space, and keeps our infrastructure costs down. We'll get into a bit more detail in the next set of slides on the function of each cluster type in this architecture.
All right, so there's a lot going on in that diagram, so I'm going to break it down so it all makes sense. Let's start with the infrastructure clusters. These are bare metal OpenShift clusters with 3 control nodes and 3 workers, and each of these clusters occupies a different physical rack connected to 2 top-of-rack switches for high availability. These are purpose-built clusters to host the VMs of the tenant clusters via OpenShift virtualization. Now, an infrastructure triplet is just a set of 3 infrastructure clusters, and each triplet can host up to 234 VMs. The tenant cluster has virtualized control nodes and bare metal workers. The control nodes are VMs running on the infrastructure triplet. Application teams procure the right size workers for their workloads. So since they don't have to worry about the control plane, this is a bring your own compute service model. So how does it all fit together? The individual infrastructure clusters act as an availability zone. Each tenant cluster control node is scheduled on a different infrastructure cluster. So that means that even if an entire infrastructure cluster goes down, the tenants where the applications live lose only a single control node. We have automation that can rebuild this infrastructure cluster and restore the control nodes within a couple of hours. And this is exercised regularly since rebuilds is how we do our upgrades. This efficient model allows for smaller tenant clusters that are more manageable and have a smaller blast radius in case of failure. And before anybody asks, yes, this is a supported solution, even though it's not documented.
All right, so the third cluster type is called prime cluster. Prime cluster are standalone clusters that are deployed in racks that we call prime. And each data center has gets one prime cluster. So from an automation perspective, prime clusters are important because they host both Ansible automation platform and the Red Hat advanced cluster management. We're going to cover RACM a bit. The Ansible automation platform is used to deploy Kubernetes clusters, and all infrastructure and tenant clusters are configured by services that run on those prime clusters. The second main component is RACM. So we use RACM to manage policies, to install operators, and also custom workloads. Any changes to the Ansible automation platform or to the advanced cluster management needs to go through a code-based workflow, and so everything stays consistent.
Okay, now let's talk about how we manage to scale the management of all these clusters. We have a strict GitOps deployment strategy, and every operation performed around cluster management must be defined in code. We use different tools for deployment and management of OpenShift clusters. Ansible Automation Platform is used for deployment of a cluster. Ansible is great for creating a provisioning workflow to allow us to build a cluster which requires many interactions with different internal systems during the build process. Systems such as DNS, IP management, CMDBs, load balancers, storage systems, and much more. We also use ACM to deploy any additional non-core components that come up once a cluster is built and handed over to our customers. Components such as external DNS, internally developed webhooks, locks and metrics forwarding, gatekeeper, and much more.
We have created an internal CMDB designed for the MKS platform called Unimatrix. We are going to cover Unimatrix during this presentation, but from a deployment perspective, our automation requires integration with Unimatrix so we can validate data such as cluster environment, what rack and hub that cluster belongs to, DNS grid assignments, and cluster ownership information. We also integrate with our change management system control. So we need to ensure that the change for that cluster has been approved and that the work window for that change matches with the execution time. Moving on with the deployment workflow, we integrate with hardware and network APIs. So the hardware API is used to collect metadata about components such as disks, the boot order, and also to manage the server power state. We then integrate with network API, so we can collect information about the top of the rack, switches, subnets, VLANs, and so on. With the network information collected in the previous step, we integrate with our DDI infrastructure. So for tasks like DNS resources allocation, DHCP settings, and also PXE. Once we have the required DNS records, we integrate with a load balancer API to create entries required by the Kubernetes API. We then configure authentication and we store users' persistent volumes in an automated way. We are going to talk more about the pview store process later in the presentation.
And the final step for the Ansible automation is to register the cluster with Red Hat Advanced Cluster Management. We have lots of day 2 configuration that are applied to the cluster, including firm policies, installation of OLM operators such as OpenShift virtualization and OpenShift logging. ACM provides us with a fast and effective way to update components, provide patching in use cases where vulnerabilities that can be mitigated without platform version updates. Finally, ACM deploys Flux, which is part of our application GitOps strategy. Based on namespace ownership and cluster ownership, Flux deploys the applications that are supposed to be part of that cluster automatically. We have end-to-end automation to rebuild clusters, restore persistent data, and deploy applications. In case of failure, the time to recovery is predictable since it's a repetitive nature of the automation.
Okay, I would like to shift our focus now to GitOps and how it's been core to our strategy and on how we approach cluster management. On the platform side, we use ACM to deploy any cluster changes that are considered non-structural. Anything outside of OpenShift platform, CNI and CSI are done through ACM because the release cadence is much more frequent. We have a 3-week release cycle in ACM for deploying changes across all 400 clusters, but we also have the ability to deploy changes within hours. With ACM, We're able to keep our clusters compliant with what we have in source control. It remediates any out-of-band changes, and it helps avoid any config drift. With Flux, our customers are able to deploy and manage all their workloads. This guarantees them consistency and the ability to recover their workloads in case of a cluster rebuild. We have an engineering lab that is set up to be representative of our production environment, which includes the compute, network, storage, and tooling. We also use KubeVirt to allow our engineers to deploy virtual clusters, which includes the control and worker nodes. Having a fully virtualized lab environment enables development velocity, deployment of test automation, and avoids any of the common challenges when sharing clusters.
So we've mentioned about how Unimatrix is used as a CMDB during cluster deployment, but it has more rules than that. So Unimatrix idea is based on a requirement to create a common experience for developers between Kubernetes on-prem and also the public cloud. And this common experience came in the form of this tool called Unimatrix. So Unimatrix abstracts the infrastructure, so developers, they don't need to worry about the infrastructure. It is a single control mechanism, and it manages lots of things in KS. For example, ownership, entitlements, logins, namespace management, and feature installations.
So we've been in this journey for over 6 years now, and we've come across some interesting challenges that we have either addressed or actively working on. There are 3 areas that I would like to highlight. In-place upgrades were a big challenge because we couldn't guarantee a successful upgrade due to the complexity of the platform. The second thing is the SRE team was executing Ansible playbooks manually, and this created a lot of toil for them. And the third thing was the recovery of data after a cluster rebuild for stateful workloads was a real challenge.
So as we said, initially our application deployments were all manual, so we had to do in-place upgrades to keep the applications up. But once we had a good onboarding pipeline for GitOps for applications, we switched over to doing rebuilds instead of upgrades. This saved us a lot of engineering time, and also provided further configuration consistency. And for managing the breakneck pace of OpenShift development, we switched over to using EUS releases. They get released every 8 months. That means we only have a single Y release hop to our next platform version. And in the odd year, we have 2 Y release hops for our next version. The rest of the updates are Z-Stream updates for bug fixes and CVEs. So let's talk about SRE toil. Back in the days, SREs, they needed to manually run Ansible playbooks and monitor them. So today, with the Ansible automation platform, they can launch dozens of deployments in parallel, fully automated. We are now developing a self-service tool that will allow cluster owners to update their own clusters without SRE intervention. And if something goes wrong, SRE team will be automatically notified and also engaged. And finally, to ensure that things are as expected, we also built a set of pre- and post-deployment checks to validate cluster deployments. So what about stateful workloads? Because, as we already mentioned, our cluster upgrade strategy involves rebuilds. We needed a way to ensure that stateful workloads could be safely restored after rebuilds. So we built a solution for that, and that solution automatically restores persistent volumes after a cluster rebuild. So no manual steps are required, which makes the rebuild process safe.
So our theme for next year's roadmap is around virtualization, all based on KubeVirt. We'll be working on a general purpose compute virtual machine platform to host virtual machines. We will also be building a virtual machine spot capacity service. This would allow other compute platforms in the bank to use unused capacity on existing Kubernetes clusters. And the last thing is we're going to be virtualizing Kubernetes clusters for certain use cases. So in summary, there are 2 key points that I want to highlight. One is thinking about scale through architecture, technology choice, and automation have been key pillars for us. And the last thing is GitOps for cluster management and application management has been core to our automation strategy. Thank you.
Go to the mic right behind you.
What's your storage backend that you're using for the infra clusters, prime cluster, and?
So you want to take that, or?
For infra clusters, we use just host path storage. We'll probably be shifting to LVMS soon, but we don't need anything that can live migrate, or we're just looking for pure performance because of etcd. Because these are specifically built clusters to host tenant cluster control nodes. We just needed performance. And we didn't, because essentially we treat them as ephemeral workloads, because they can be destroyed and rebuilt at will. We don't really need any kind of fancy CSI for the infra clusters. For the tenants, for our customers, we use a NetApp array with the Trident CSI.
So you divided workloads into custom workloads and I think application workloads, and the custom workloads were deployed via ACM. How do you decide whether to use ACM to manage deploying workload versus, I think it was Flux, to deploy the workload? How do you differentiate the two different classes?
So I'll take this one. So initially we made an architectural choice, right? So we do have Kubernetes clusters on-prem and off-prem. So we wanted a tool that would give our developers a consistent experience from a GitOps standpoint. So Flux was the natural choice for that for us. For ACM, that applies for any of our on-prem clusters in terms of how we deploy changes onto them. Anything outside of the OpenShift platform itself, the CSI and CNI, and because we have a 3-month release cycle for engineering every release, we needed to sort of guarantee that we could do that safely. Anything that it's more frequent, that's where we use ACM, like external DNS as an example, right?
I might have the perfect follow-up question. Thank you for sharing so much information about what y'all do. That's really helpful. You'd made a comment about ACM being used to maintain the clusters, but you said it didn't make structural changes, or you didn't use it for structural changes. Can you differentiate what would then fall out of scope into that bucket? Thank you.
Yeah, so the OpenShift platform at our bank takes to download these images about a month and a half. We have membership from our networking team, and they take about 3 weeks to do proper sort of testing certification on our CNI, which is Calico. We treat Calico as a network device, so we do a full certification of it. We run over 200 tests. Some of them are manual, some of them are automated. We also do certification on the NetApp storage. So we consider those core structural components because we do have to do a long engineering cycle to make sure that we can guarantee the stability of the platform, right? So that's what we consider structural. Anything outside of those 3 components are non-structural, and usually are backwards compatible.
Okay. Why did you choose rebuilding the cluster instead of in-cluster upgrade? Is there a reason for that?
Consistency. So we have now over 400 clusters out there. Having automation that handles OpenShift, Calico CNI, Trident for storage, and the various integrations that we have. Having an automation that can consistently have successful upgrades across all clusters was key, and it took a lot of engineering effort to do that. And because the things that we're super allergic to SRE toil. So we want to create the least amount of toil with configuration consistency. And rebuilds were a great way to do that. Rebuilds were also a great way to validate that a cluster can be recovered in case of failure, right? So we didn't want people to see these places as, oh, you know what, I can do application changes and I don't need to keep track. No, a cluster can be rebuilt, application needs to come up exactly as it was before. And a rebuild is a great way to exercise those automations.
Yeah, if I can add to that. So one of the things that we've done as well is that we built some sort of signature into our clusters So we know when it was upgraded, right? Upgraded means rebuild for us, any changes deployed to it. So we know exactly what build that cluster has. And if there's an issue with that cluster, we typically don't troubleshoot those issues there in production. We're able to recreate those issues. For the most part, we create those builds in the lab because of that, right? Or else every cluster becomes a snowflake if everything is in place upgrades.
Managing these many clusters, like how do you load balance the traffic, if you always rebuild the new clusters?
So we have we made a choice from an architecture standpoint with our customers. We basically said to them that they're responsible for the application architecture onto those clusters. So for us, we treat them as standalone clusters, but then our customers do have patterns for how to architect their applications on top of those clusters, whether they're homegrown applications or third-party systems. There are patterns that we have for how to leverage that. So they would know if they have 2 critical clusters in 2 different data centers, right, that they would have to do one cluster first in terms of the rebuild, or their traffic, whatever their application architecture is, would have to survive with that other cluster, or they have the freedom to go and choose, buy as many clusters as they choose in whatever location we support them.
And one of the things that really this rebuild achieves is, because as you scale out, you need more people to support the infrastructure. So from a time where we're only in like a couple of dozen clusters to now time we're over 400 clusters, we've barely grown the SRE team because of trying our efforts to keep the toil at a manageable level. And that feeds into our kind of roadmap. Now, even for launching the AAP automation to rebuild clusters, we're working on self-service, which means the cluster owners themselves will initiate the cluster upgrades, and SRE won't even know about it until if something bad happens and they have to get involved. But otherwise, it'll be transparent to them. Right now, there's a lot of time involved in coordination between SRE and customers, trying to figure out time windows and change management, which the customer can do by themselves.
Okay, we have 2 more people lined up for questions, and then we will move on.
Thanks for the presentation. I have questions regarding the infra clusters. You guys are using KubeVirt to do the VMs. Any consideration using hosted control planes, or there are pros and cons or any compliance issues right now?
I can
So I
take that
can
one.
answer that. This was cooked up way before hosted control planes was a thing. But one of the things with hosted control planes is it doesn't address our failover domains. So hosted control planes failover domain is a single OpenShift cluster, while we have 2 clusters being the failover domain in this design. And one of the things with hosted control planes is that for density on bare metal, this actually provides us with more density. So per infrastructure node, we have 26 control plane VMs on there. You would hit the pod limit in most cases way before that for hosted control planes. For hosted control planes, you have about 70 pods per cluster being spun up, and you would hit, even if being generous, 500,000 pod limit, you would hit that before you reach the same density as this design. So at scale, this makes really great sense, especially since we already put the engineering effort to automate everything. If you're starting from scratch, you could probably design something nice around hosted control planes, perhaps not at this scale.
You want to add something else?
Just a question, with so many clusters and rebuild needed, how do you manage like the observability, the alarming? Are you handling all on the SCM only? Because I know like the SCM provides some unique stacks for monitoring, or do you use other components outside of this for logging metrics and stuff?
I'll take it. So we don't use the ACM sort of functionality in terms of observability. We have a different team within our department that focus primarily on observability. So they have a stack, they call it central observability, sort of feels and looks like Rackham, but it's got many other components. every metric, every log on every cluster, it flows to that system. Whenever we do any sort of maintenance on our clusters, we do have tooling to be able to put those clusters in maintenance mode, so they could disable any alarms, any alerts to our applications or support teams.
Okay. And just as customers needs to rebuild, if you trigger an update, you don't trigger update, you rebuild from scratch. Is there like for the cluster, I mean, is there a way you manage like the persistence of the observability for these clusters as like they disappear and you rebuild them, or?
Yeah, I think what's great about the technology choices that we made is that the persistent storage is outside of the cluster.
Mm-hmm.
So the data stays there. When we rebuild the cluster, well, just the references to that data is gone.
Yeah.
So we built automation to be able to recreate those references for all those PVs and PVCs onto those clusters, but the data stays.
Thanks.